In this final week of this course, we will state and prove a very classical theorem from complex analysis called Picard's theorem. Very broadly, Picard's theorem tells us that if you consider a non-constant entire function, then its image doesn't miss too many points. We will make it concrete and state and prove the Picard's theorem in due course. However, before that, let's develop some machinery which is needed to indeed prove Picard's theorem, namely that of covering spaces. In this lecture, we will define what is meant by the lifting property of maps, and we will prove some properties of lifts. So let me start by defining what is meant by lifting. Let's start with x, y and z be open connected subsets of open subsets. No need to impose the condition of connected yet. Open subsets of C, and let f from x, maybe y to x, and g from z to x be continuous maps. If I have to capture it in an image, what we have is this following map f from y to x, and we also have the map g from z to x. We say that a map g tilde from z to y, let me just draw that as well, it's going to be in this direction here. G tilde is a lift of g with respect to f. So that's the thing that we are defining. It's a lift of g with respect to f if the diagram commutes. What is the meaning of that? That means that f composed with g tilde is equal to g on, this is a tilde here, is equal to g on z. Means if you go in this direction and if you go along g, we are going to end up with the same element in x. So if this happens, then we say that g tilde is a lift of g with respect to f. We have already seen lifts in disguise earlier. Let me give you an example to reveal the disguise. Consider the following map. F is going to be the exponential map. Consider exponential from C to C star. So here y is going to be C, x is going to be C star, and let omega be some simply connected subset of C star. Let omega be simply connected subset of C star. So the image is going to be now like this. There is C here, there is C star here, and the map here is exp. And if you look at omega, which is the identity map now, or rather omega is a simply connected subset of simply connected open connected subset of C star, and therefore you have the identity map, which is the inclusion map. Then let f, oh I have already taken f, so let's call it I tilde just to be consistent with the notation, be a branch of the logarithm which is holomorphic on omega. What does that mean? I.e., if you look at x composed with identity tilde, that's just going to be of z, identity tilde of z, that's going to be equal to z, which is the same as identity of z, right? This is precisely what it means for identity tilde to be a branch of the logarithm. But what does the condition manifest here as? If you look at the identity tilde as a map here, what it tells us is that this particular diagram commutes. So in other words, what we have just realized is that the branch of a branch of the logarithm, in fact we didn't have to impose the condition of holomorphicity, we just needed a continuous branch and it would have turned out to be a lift of the identity map. So hence a branch of the continuous, let me just say that continuous branch of the logarithm is a lift of the identity map with respect to the exponential. That's precisely what we have realized as. If omega were not a simply connected domain contained in C star, if omega was some other open connected subset of C star, we do not know about the existence of the lift of the identity. It's again another way of saying that we do not know about the existence of continuous branch of the logarithm. But in this case, when omega is a simply connected domain contained in C star, we do have at least one explicit branch of the logarithm. That is good because we now have an example, and we also know more about such lifts. We know that if there are two continuous branches of the logarithm, then they should differ by a 2 pi I k. And if f is a lift of the identity, if it is a branch of the logarithm, then f plus 2 pi I k for some fixed k is going to be another branch of the logarithm. So we certainly know that these lifts cannot be unique. For every k in integer, we are able to get hold of one such lift, right? But nevertheless, we still can say something about uniqueness of such lifts, which is going to be the content of the next theorem. Let me just write it down as a theorem. Uniqueness of lifts. So notice that our exponential map here is a very powerful map, in the sense that on C, if you look at the derivative of the exponential map, which is again exponential, it is non-zero. So at every point we do have that the exponential is a local homeomorphism. That's certainly there. We did not demand any such condition on f. So you could have had f a little more general and the definition still holds, but we will be only dealing with local homeomorphisms in this lecture. In fact, we will be dealing with something more stronger over a period of time. We will define what is meant by a covering map. We will come to all that later, but we will certainly impose the condition of local homeomorphism that we are going to deal with. So let x comma y be open connected subsets. Yeah, we don't need connectedness here, so let me not impose that. Open subsets of C, and f from y to x be a local homeomorphism. The above example fit perfectly here. What is the formal definition? Local homeomorphism means the following, i.e. given a point y not in capital Y, there exists neighborhood v of y naught and u of f of y naught. So this is in capital Y and u of f of y naught in capital X, such that f restricted to v from v to u is a homeomorphism on to u. Recall that a homeomorphism is just a continuous map with a continuous inverse. So in particular, it's necessarily a bijective map. So this is a local homeomorphism, means that locally it's going to be a homeomorphism. It need not necessarily be a global homeomorphism. For example, this particular case that we were considering, exponential, is certainly a local homeomorphism thanks to the inverse function theorem that we have proved earlier. Because its derivative does not vanish, we can get hold of a small neighborhood. So I'll just call the neighborhood V and U, reversing the notations used earlier, such that when X is restricted to V, it's going to be an injective map. It's going to be a biholomorphism, in fact. In particular, it's going to be a homeomorphism. Another example is the map Z going to Z to the power n in the punctured disk, for example. For any n greater than or equal to 1, for n equal to 1, it's a homeomorphism. For n greater than 1, it's a local homeomorphism, which is not a homeomorphism. It's not a homeomorphism because it's not going to be injective on the unit, punctured unit disk. Yeah, so that's what the context is. We are going to consider only local homeomorphisms. Okay, the theorem now says the following. Let Z be a connected open subset of C and G from Z to X be a continuous map. Suppose we have two lifts of G with respect to F. Let G1 tilde and G2 tilde be lifts of F, lifts of G with respect to F. What does that mean? It means that F composed with G1 tilde is equal to G and F composed with G2 tilde, that is also equal to G. So we have two lifts of G1 of G with respect to F. And suppose these two lifts agree at one point. Suppose G1 tilde of say Z0 is equal to G2 tilde of Z0 for some Z0 in capital Z. Then the theorem tells us that G1 tilde is identically equal to G2 tilde. That's what the theorem tells us. So let me just go over the theorem for you once. Spent quite a lot of time trying to recall what a local homeomorphism is. So let me just focus on the theorem now. Suppose we have two open subsets of C, Y and X. And suppose we have a map F from Y to X, which is a local homeomorphism. Notice that we have still not introduced holomorphicity anywhere yet. We will do that in a minute. We are just considering continuous maps. So here in this case, F is a local homeomorphism from Y to X. Suppose we have a map G, which is a continuous map from some other open connected subset Z of C into X. And suppose we have two lifts of G, G1 tilde and G2 tilde. The uniqueness theorem tells us that G1 tilde and G2 tilde, if they agree even on one point, they have to be identically equal on the entire space Z. Let's give a proof of this statement. It's a trick that we have, it's a technique that we have used multiple times earlier. Let's start by capturing all those points where G1 tilde and G2 tilde coincide. Let's call that set something. Let E be the set of all Z in capital Z such that G1 tilde of Z is the same as G2 tilde of Z. What can we say about such a set? The first thing that we can say is that it is non-empty because the point Z0 here is already in the set E. That's the first observation here. Notice that Z0 belongs to E, and further if you look at E, it's just the pullback of 0 under G1 tilde minus G2 tilde. And since E is equal to G1 tilde minus G2 tilde inverse of the singleton set 0, it's closed. Remember that we have put a condition of connectedness on the set Z, which we are going to use very crucially here. If we manage to show that our set E is an open set as well, then what we would have obtained is a separation of Z, which is non-empty. The point Z0 belonging to E ensures that it's non-empty, and the fact that it is both open and closed will tell us that it is a separation until and unless it's the entire set, and therefore it will be forced that E is equal to Z, thereby proving our result. So let me just state our claim which will establish this result, E is open in Z. And to prove this, let's pick some arbitrary point. Let Z be a point in capital E. Let me draw the diagram here for you. Y to X, we have our map F, we have the map G from Z to X, and we have two lifts, G1 tilde and G2 tilde. Both of them satisfying the condition that Z0 is being mapped to the same point in capital Y. Now Z is going to be a point here, and because it's in E, since Z is in E, that means that G1 tilde of Z is the same as G2 tilde of Z by the very definition of E, right? Let's call that point something, let's call it Y. So this point is getting mapped to, let me use a color to capture that. Let me use red to take a point Z here. That's getting mapped to the point Y here, and under F, let it get mapped to the point X here. And by the very commutativity, G is going to map Z to X. Let X be equal to F of Y. Now, we have not used the fact yet that our map F is a local homeomorphism, and because F is a local homeomorphism, there X is a neighborhood of small y, let's call that V, and a neighborhood of X, let's call that U, says that F restricted to V from V to U is a homeomorphism. Since F is a local homeomorphism, there X is a neighborhood V of Y and U of X, which is F of Y in Y and X respectively, such that F restricted to V from V on to U is a homeomorphism. In particular, what we have is that this map F restricted to V has an inverse. Let phi from U to V be the inverse of F restricted to V. Always keep in mind that we only know that F restricted to V is a homeomorphism. So the inverse is also locally defined. It's defined from a neighborhood of X to the neighborhood of Y. Okay, so now what do we have? Since G1 tilde and G2, before we progress further, we also know that G1 tilde and G2 tilde are continuous functions, right? So since G1 tilde and G2 tilde are continuous, if you pull back capital V, that's going to be open for both G1 tilde and G2 tilde. Pullbacks under G1 tilde and G2 tilde both are going to be open, and therefore its intersection will also be open. G1 tilde pullback of V intersected with G2 tilde pullback of V is open in Z. In particular, our point Z is an interior point, and let W be a neighborhood of Z such that W is contained in G1 tilde inverse of V intersected with G2 tilde inverse of V. This can always be arranged. So let me just draw a few pictures for you. So suppose this is our Y, and suppose this is our X, and suppose this is our Z. What was done was, we had a point here which was say Y, and this is our V, and let me shade it in red. That was getting mapped to the point X here, and the set V was getting mapped to U. Now there is the map G here, there is the map F here, there is this map G1 tilde, and there is this map G2 tilde. where all these diagrams commute. If you pull back our G inverse, G1 tilde inverse V, we end up with some set like this, and so this is going to be under G. So let me just map this with purple, and let me use blue to capture G2 tilde. So this is going to be the purple, which is capturing G1 tilde inverse of V, and the blue will capture G2 tilde inverse of V. And somewhere in this intersection, which is being captured by, so this is the point Z was here, let's say, and the orange is some neighborhood which is contained in the intersection. So that's precisely going to be our W. So this is going to be, let me give the names to this. This is going to be G1 tilde inverse of V. This blue is going to be G2 tilde inverse of V, and the orange is precisely the W. Okay, so that's the picture that was captured very concretely above. And notice that G1 tilde of W and G2 tilde of W both are contained in V. That is the primary observation here. Then, because of the very construction, what we have is that if you look at G1 tilde restricted to W composed with F, that's going to be equal to F restricted to V composed with G1 tilde of W, primarily because W is mapping inside capital V, or rather W is mapped by G1 tilde into V, and therefore we just need to focus on this. And we know that this is just equal to G restricted to W. Similarly, G restricted to W is also the same as F restricted to V composed with G2 tilde restricted to W. Now here, by composing with phi on both sides, we get G1 by, let me write it down. G1 tilde restricted to W is the same as phi composed with G restricted to W, which is the same as G2 tilde composed with W. And therefore, what do we have? Hence, G1 tilde is equal to G2 tilde on W. That implies that W is contained in E, and therefore E is an open subset of W of Z. And by the very definition of connectedness, since Z is connected, it cannot have a separation, and E is equal to Z. So we have concluded that if two lifts are equal at a particular point, then they necessarily be equal on the entire topological space, on the entire open connected set Z of C. So till now we have not addressed the case of holomorphic maps. We have only dealt with continuous maps till now. Let's address that issue now. Let's try to specialize to holomorphic functions. That's going to be done by this theorem. Let's take some holomorphic map. Let f from y to x. So the y and x are open subsets of C. I have not put any more conditions there. Why f from y to x be a holomorphic map such that the derivative of f doesn't vanish at any point of y, so that f prime of y is not equal to 0 on capital Y. This ensures that at every point of capital Y we can establish f as a biholomorphism, local biholomorphism. We can, given a point y in capital Y, we have a neighborhood by the inverse function theorem which maps holomorphically onto its image in capital X, which will be an open subset, and it will also have a holomorphic inverse. So this is going to be a local biholomorphism. Now let G from Z to X be a holomorphic map such that G tilde from Z to Y is a lift of G with respect to F. Remember that when we talk about a lift, we are only demanding that such a lift be continuous. The theorem tells us that G tilde is holomorphic. If you indeed have a lift, then it's necessarily going to be a holomorphic map. Let's give a proof of this. The first observation is that since f prime of y is not equal to 0, for all y in capital Y, f is a local homeomorphism which is holomorphic with holomorphic inverse. Going to use that very crucially. Let's again draw pictures. We have y, we have x, the map here is f, z to x is the map g, and we have a lift g tilde. Our goal is to show that it's holomorphic on z. Holomorphicity is a local property. We will show that it is holomorphic in every around every point in z. So let's fix a point z here. Z be in capital Z, y be equal to g of z, and x be equal to f of z. Okay, sorry. So y be x be equal to g of z, and y be equal to g tilde of z. Let me just use red to denote all that. Z is a point here. Z is getting mapped by g tilde to a point y here, and it is getting mapped to x here. So the map G takes Z to X and the map F takes Y to X because of the fact that G tilde is a lift. Now, because F prime of Y doesn't vanish, by the inverse function theorem, let me use that, by the inverse function theorem, there exists a neighborhood. I'm going to call the neighborhood V of small y and U of small x. Remember that x is f of x, such that f restricted to V from V to U is biholomorphism, holomorphic map onto U with holomorphic inverse. Let's call that inverse phi. So phi, which is now from U to V, right? So let W now be equal to F inverse of V. Now, if you look at W, that's neighborhood of Z, and on W we have, I'll just write directly that G tilde is just going to be equal to phi composed with G. This is on W. I'll just leave it at this. By a very similar argument as in the previous theorem, we can conclude that this is the case. And both G and phi are holomorphic. Since G and phi are holomorphic, we have G tilde is holomorphic on W. And therefore, we have established that given any point, we have a neighborhood where our map G tilde is holomorphic, which tells us that G tilde is holomorphic on Z, and that's precisely what we were trying to prove. So this theorem is quite powerful in the following sense. If we have a function which holomorphic function which has a non-zero derivative at every point, then every lift of a holomorphic function should, with respect to this function, should necessarily be holomorphic. And that's something which we would desire. So automatically, if you consider the exponential function, for example, that satisfies the condition that the derivative does not vanish, and therefore if we look at the lift of the identity map here, that will necessarily turn out to be a holomorphic map. So the question of obtaining a holomorphic branch of the logarithm, in some sense we have reduced it to getting hold of a lift of the identity map with respect to the exponential map. Alright, let's now try to see what happens when we lift curves. Curves are very special objects for us, and we would like to see what happens when we are lifting curves under such good maps like, say, local homeomorphisms. The uniqueness of the lifting tells us that if you prescribe the initial point of the lifting, then the lifting has to be unique of a curve, right? So suppose gamma from, say, AB to X be a curve, and gamma tilde from AB to Y be a lift of gamma with respect to F. So the setup is as earlier, I am not rewriting it. Suppose this is the case, then the curve gamma tilde is unique if we prescribe the initial point. By the uniqueness of the lifting that we mentioned a few minutes back. We can say more about lifting of curves. In fact, we will now prove a theorem which says that homotopic curves, if at every stage it can be lifted to a curve starting at the same point, then the lifted curves will also be homotopic. Let me just write that theorem down and make it precise for you. We're going to go back to the setup of a local homeomorphism. Let f from x to maybe y to x be a local homeomorphism between open subsets of C. And suppose we have gamma 0 and gamma 1, let gamma 0 and gamma 1 be curves in X from some point, from initial point, say Z1 to Z2, which are homotopic with fixed endpoints, Let's also tell what the homotopy is through the map, say H, which is from 0, 1 cross AB into capital X. It's the usual homotopy from gamma, it's the usual definition of the homotopy from gamma 0 to gamma 1 that will be applied to capital H. Now further, suppose for every S in 0, 1, if you look at gamma S of t is which is given by h of s comma t for t in AB, can be lifted to a path, say gamma s tilde from AB to Y with respect to F, such that gamma s tilde of A is equal to some, say, Z1 tilde for all S in 0, 1. That means what we have done is that at every stage gamma s is being lifted. We are given that it can be lifted to a curve in capital Y which originates at the same point Z1 tilde. Remember that because this is a lift, Z1 tilde has to be a pre-image of Z1, where Z1 was the initial point of both gamma 0 and gamma 1. So the gamma s are all special. Gamma s are such paths which can be lifted. We are given that, that's there in the hypothesis. The conclusion is that then gamma 0 tilde and gamma 1 tilde are homotopic with fixed endpoints in capital Y. Let me just draw the picture for you to make things clear. We have our x here and we have our y here, and suppose we have a homotopy of curves. Let's say this is our z1 and this is our z2. The image will make it much clearer, and suppose this is some gamma s. So let me name all these things. This is gamma 0, this is gamma 1, and this is say gamma s. And suppose we are able to talk about the lift. This is say gamma 0 tilde, this is say gamma 1 tilde, and say this is going to be gamma s tilde. What this says is that, so the point here is going to be z1 tilde. Z1 tilde is getting mapped under f to z1, and gamma f composed with gamma s tilde is equal to gamma s. That's what it means for gamma s tilde to be a lift of gamma s with respect to f. All this is getting satisfied, then what is being claimed is that gamma 0 tilde and gamma 1 tilde are going to be homotopic to each other. We don't know whether it ends at the same point or whether the natural definition of the homotopy that we will be defining is going to be continuous. So that's going to be the goal while we try to prove it. The natural definition is going to kick in for the homotopy, which will be our first guess. Define h tilde from 0 1 cross AB into capital Y given by h tilde of s comma t is equal to gamma s tilde of t. It's not even known whether this map is continuous. That's the first goal. In fact, the most difficult part is going to be to show that this is indeed continuous. But before we get into it, in fact, let's try to prove that this is a continuous map. To do that, let's observe that since f is a local homeomorphism, that's how we started off with, right? There is a local homeomorphism here between y and x, right? And because it's a local homeomorphism, we can get hold of neighborhoods of z1 tilde and z1 such that the restriction is going to be a homeomorphism. Let v comma u be neighborhoods of z1 tilde and z1 respectively, such that f restricted to v from v to u is a homeomorphism. Now our map capital H is a continuous map, and if you observe H inverse of capital U is an open subset of, well, where is capital H from? It's going to be from 0 1 cross AB, right? H of s comma a plus epsilon, which depends on s, is going to be contained in U, and by a compactness argument, I'll just give it as an exercise here for you to sit down and check that by compactness of 0 1 and continuity of H restricted to 0 1, maybe continuity of H is enough, we have an epsilon positive H of 0 1 cross a plus epsilon open. This open set is contained in capital U. Some neighborhood, this is some neighborhood, we don't need to use compactness, we just need continuity of H actually. Yeah, this is going to follow by the fact that at 0 comma 1, the tuple 0 comma 1, the function H is continuous. Oh, we do need compactness, so let me keep it as such. So again, think about why compactness is being put into the exercise. We do have an epsilon which satisfies the condition that 0 1 cross a plus epsilon is mapped to within U. Now if we use the fact that gamma s tilde of f of gamma s tilde of t is equal to gamma s of t for s comma t in 0 1. It's true in 0 1 cross AB, but let's focus on 0 1 cross A comma A plus epsilon. F composed with gamma s tilde of t is equal to gamma s of t. And by composing with the inverse, did I put an inverse here? Is a homeomorphism. Let me just give the inverse with inverse given by phi from u to v. And yeah, because this is getting mapped to within v by composing with phi, which makes sense, we have h tilde of s comma t is equal to phi composed with gamma s of t, which is just phi composed with h of s comma t. This just tells us that h tilde restricted to 0 1 cross a epsilon, a plus epsilon, this is continuous. Let's now prove that h tilde is continuous on 0 1 cross AB. Suppose h tilde is not continuous on 0 1 cross AB. Let's pick a point S naught in 0 1 and let T naught be the smallest point at which h tilde is not continuous. H tilde of S comma T is not continuous. Let me just write that down. Suppose h tilde is not continuous. And given some point S naught in 0 1, let T naught in AB be such that h of S comma T naught is, h is not continuous, rather h tilde is not continuous at S0 comma T naught, and h tilde is continuous for all t less than T naught at S naught comma T. Is continuous at S naught comma T. So the first observation is that this T naught is going to be greater than or equal to epsilon. That's the first observation. That let me not note that unnecessarily. The first observation is that if you look at the image of S0 T0, let u, maybe I'll just keep using u's and v's. The role here of u and v is done. So this is a new u and new v. Let u and v be neighborhoods of gamma S0 of T0 and gamma tilde S0 of T0, the points where discontinuity has happened. Let's pick two neighborhoods such that f restricted to u from u to v is a homeomorphism, and we have its inverse, and phi from v to u be its inverse, which is a continuous map, which is in particular a homeomorphism again. Because H is a continuous map, since H is continuous, remember that the homotopy is a continuous map, we can get hold of some delta, there X is some delta positive such that H of, what were the points, S0 and T0. So if you look at S0 minus delta to S0 plus delta cross T0 minus delta to T0 plus delta, if you look at this neighborhood, it's mapped by H to within U. That's something which we can ensure, we get hold of one such delta. And let's pick some point t which is less than t naught in this interval. Let maybe t1 be a point in t naught to t naught minus delta. The good thing about t1 is that h tilde is now continuous at S0 comma T1. Recall that T0 was the smallest point where h tilde of S comma T turned out to be discontinuous. So any point less than that, it is continuous. So let's focus at the point S0 comma T1, and because it is continuous, there exists neighborhood, maybe there exists a delta prime positive with delta prime less than delta, certainly, such that if you look at uh, S0 minus delta prime, for S in S0 minus delta prime to S0 plus delta prime, if you look at this particular neighborhood, then H tilde of S comma T1 belongs to capital V. Notice that we have crucially used the fact that H tilde is continuous at the point S0 comma T1, and also the fact that H tilde of S0 comma T1 belongs to V, and that is the reason why we have one such delta prime. So you can pick a delta prime which is less than delta, which will be clear why that is being done. Now if you consider S0 minus delta prime to S0 plus delta prime cross T0 minus delta to T0 plus delta. If you consider this particular gamma S tilde restricted to T0 minus delta to T0 plus delta, this is a lift of gamma S restricted to T0 minus delta to T0 plus delta. Also, we also have one more lift. Also, if you look at phi composed with gamma S restricted to T0 minus delta to T0 plus delta, that is also going to be a lift of gamma S restricted to T0 minus delta to T0 plus delta. So, there are two lifts of gamma S now, and moreover we have just ensured that at the point T1, at the point S0 comma T1, we have gamma S tilde of S0 comma T1 is the same as phi composed with gamma S of S0 comma T1. Now that's because we just ensured that H tilde is going to be here. Now we apply the uniqueness of lifts to this particular interval. We see that if two lifts are going to be equal at one point, they have to be equal in the entire neighborhood, in the entire domain, and therefore we get to conclude that gamma S tilde restricted to S0 minus delta to delta prime to S0, sorry, T0 minus delta to T0 plus delta. This is equal to phi composed with gamma S restricted to T0 minus delta to T0 plus delta, which tells us that H tilde of S comma T is equal to phi composed with H of S comma T for S comma T belonging to S0 minus delta prime, S0 plus delta prime cross T0 minus delta to T0 plus delta. This is precisely what we have established. But that's a contradiction. What is the contradiction? The contradiction is that we had assumed H tilde to not be continuous at S0 comma T0, but the thing on the right, phi composed with H, is a continuous map. Since phi composed with H is continuous at S0 comma T0, we have H tilde, we have a contradiction, and therefore H tilde should necessarily be a continuous map. That's the starting point of all this, right? Suppose H tilde is not continuous. So in particular, H tilde has to be continuous. Contradiction. Hence H tilde is continuous on 0, 1 cross AB. So what have we just established? We have just established that the map H tilde that we have defined, where was the map? This is the map that we defined. This map is continuous on 0, 1 cross AB. We also have that at every stage S, gamma S tilde is a lift. So it's a lift which starts at Z1 tilde. So the only thing that is left to check now is that H tilde is going to map the point, the end point rather, h tilde of s comma b to the same point. That's the only thing that is left to check to establish that h tilde is indeed a homotopy with fixed endpoints. To do that, the simple observation is that notice that h tilde of s comma b, this is going to be mapped, if you compose it with small f, that's going to be equal to h of s comma b, and at every stage that's going to be equal to z1, the end point, the terminal point of gamma s. So in particular, h tilde of s comma b belongs to f inverse of z1. Now f inverse of z1 is a discrete subset of capital Y. That is because we have assumed that f is a local homeomorphism, and therefore at every point in the pre-image we have a neighborhood where it is injective. There is no other point from the pre-image of z. So this is going to be a discrete subset of capital Y, and h tilde restricted to 0, 1 cross the singleton B is a continuous map. Let me just note both of them down. F inverse of the point z1 is discrete in capital Y, and h tilde is continuous on 0, 1 cross B, and therefore h tilde of 0, 1 cross B is going to be a connected subset of capital Y. But because f inverse of z1 and connected subset of capital Y is contained in a discrete set f inverse of z1. What can we say about continuous maps from a connected set to a discrete set? We know that it has to be necessarily constant, because otherwise we will be able to get hold of a disconnection of the image. We know that continuous maps take connected sets to connected sets, but that will not happen if we are not getting a constant. Let me just note here that h of 0, 1 cross B is hence a constant, and that's precisely the demand that gamma s tilde has the terminal point some fixed z1 tilde. So with that we have completed the lift of the homotopy. We will be using this quite crucially in the following lectures. So we have discussed lifts of homotopy as well. We will apply it to the theory of covering spaces, which we will see in the next lecture.